this week's experiment, we are making aspirin, and this is our stoichiometry lab. So just starting with a few definitions. The limiting reagent reacts completely. It limits the amount of product. Use that number to determine how much product is actually made. The excess reagent, there's more there than is needed, so some will be mixed in with the product at the end. Theoretical yield, it's calculated, but that calculation involves using the coefficients in the chemical equation. Sometimes you have to calculate an actual yield, and we'll run into that later in the class. But the key is theoretical yield involves the coefficients in the equation. Actual yield is the amount you actually weigh out. You physically weigh out in the lab. In other words, at the end of this experiment, you'll have some white powder that's aspirin, and you'll weigh it and see how much you got. And then percent yield, actual divided by theoretical. One way to think of theoretical, this is like your maximum amount possible. And that's what it really is. Anyway, and so that you see how you compare to the maximum to see how successful you were. This reaction does use a catalyst. A catalyst is usually there in pretty small amounts. The amount is not all that important. And so it usually just stays out of, or always stays out of your stoichiometry calculations. It is there to speed up the reaction, but is not really consumed by the reaction. And ours is phosphoric acid in this experiment. If we didn't use it, the reaction would take a lot longer, not the 15 minutes. Okay, this is just an example. This is not how our numbers will come up. But I have an amount of salicylic acid, an amount of acetic anhydride. The phosphoric acid is just the catalyst, so it doesn't come into our calculations. I'm putting the molar masses below, and I put the one for aspirin here. I'm going to write in the others as well. And I have the units there, so I'm going to skip that. Okay, so we need molar masses, and the first question is, how do you calculate a molar mass? So I'm just going to do one of them. You're probably really bored with these at this point. And of course, I got these numbers from the periodic table. I did use extra digits in this so that we would have 4 digits in our molar mass that we needed. But anyway. Okay, so that's how I got my molar mass. And now I'm going to determine how many moles of each reactant. I'm doing this in the same steps that your procedure has you do it. So in other words, on this one, I'm going back and looking at the amounts that I used up here, the amounts that were used in this particular experiment, and I'm going to convert them both to moles. The acetic anhydride is kind of different because it is a liquid. So instead of weighing it out, we're going to get a volume in our graduated cylinder. This is not the volume you use, by the way, but in this example. And so we need to use its density to convert it to grams. And then from grams, we go to moles using the molar mass. Okay, so let's just label it. This step is from its density, and this step is from its molar mass. And then over here, I'll write it with the correct sig figs. Salicylic acid is a little faster because we have grams of salicylic acid. Again, this was just molar mass. Okay, and our next step asks us which reactant is limiting. And to decide that, you don't look at the amounts of the reactants, you look at the amounts of products. And we want to say which one predicts less product. But this is a pretty simple one, so we can just look at these amounts of reactants and just look at them and predict how much product they would give. In other words, how many moles of aspirin would that much acetic anhydride make if it all reacted? And the reason that it's so easy is if we go back to our chemical equation, these coefficients are all 1. So it's a 1-to-1 ratio. If this number of moles of acetic anhydride reacted completely, we would get that number of moles of aspirin. And we can do the same thing. It's a 1-to-1 mole ratio. Okay, so from that, what we normally do is we look at the one that makes the least product or predicts the least product. And we see that this one, the acetic anhydride, it must be the limiting. And this is going to be our theoretical yield in moles. And this one is the excess, or salicylic acid is the excess reagent. It predicted the higher amount of product. So we decided that it was the acetic anhydride. And then we're going to calculate the theoretical yield of aspirin in grams. So I'm going to go back to this. We already kind of did this one step without showing it, but I'm going to start with my amount of limiting reagent, and I'm going to use all the digits when I do this calculation. So I'm going to start with our limiting reagent. And this step is using the coefficients, and this is the part we kind of did in our heads on the other page. But then it asked for the theoretical yield in grams, so I'm going to do another step. And this step is the molar mass of aspirin that I'm using. Okay, so this is, again, our theoretical yield. This is the max possible that could be produced from that amount of acetic anhydride is a limiting reagent. Okay, if we recovered this amount, this is an actual yield. That's how much powder you're weighing at the end of the experiment to see how much aspirin you made. And so percent yield compares the amount you actually got to the maximum amount possible. Okay, and you noticed I carried extra digits in my calculations the whole way. If you didn't, this last digit may come out a little different, or you might end up with 96.9 or something. Remember, the last digit on the right has some error. It is better technically to kind of carry some extra digits and just round off when you report an answer. Okay. Last question, can the percent yield be over 100%? Remember that the theoretical yield is the maximum possible. So you can't get more than 100% pure aspirin, but it may appear that you have more. So if your numbers come out over 100%, it probably means that you have a contaminant. In other words, you're not weighing just pure aspirin for your actual yield. The most common contaminant in this experiment is to have water left in your aspirin because we don't get it totally dry with the way we do it.